Hello, students. It's Mr. Pouts, and here's a lesson about graphing function rules. So it's chapter 4, section 4, and the goal to focus on and to write down, to think about, and ultimately, in the end, we'll self-assess ourselves about, um, is I can graph equations that represent functions. So we're really focusing on the skill of graphing function equations. We're going to start off actually with a couple of vocab terms, a couple of review ones, a couple new ones. So the two review ones that we're going to talk about are linear functions and nonlinear functions. Now you know that from this that these linear functions they graph lines. So a linear function is a function whose graph I should say whose graph is a non-vertical line. And the example over to the right is a picture of one. All right. So a function whose graph is a non-vertical line. That word line is the root word of it. Now, if we're talking nonlinear, that's the opposite. It's a function whose graph is not a straight line. So anything that has curves or V shapes or anything like that, that would be nonlinear. We're going to do graphs of both of those today. Now, something that we're going to get to in the second part, probably not in this video, but maybe in the second day of our lesson, um, just as we're finishing up, talking about the difference between continuous and discrete graphs. And I wanted to show you it now because these are in this section. Continuous graphs are graphs, most graphs are continuous that we're going to be working with. It's a graph that is unbroken. So if you look at this one, it's never broken. It's just a straight line. This one is not broken. It continues forever. Um, Even this one here, it's continuous. I guess it's the same one as the one down here. But those are all continuous graphs. And the difference between continuous and discrete graphs are that discrete graphs are broken. So they're composed of distinct isolated points or just broken up points. There are some certain instances, some certain real world situations that that would not be continuous. They would just be graphed by the individual points. And you'll see more of that next year in Algebra 1. You'll also see more of that if you ever take statistics or you deal with statistics at all in life. Those are graphs you'll see there. So let's start off. Let's just read through something that you need to know, something that kind of helps us understand some of today's stuff. It says the set of all solutions of an equation forms the equation's graph. So all the solutions of an equation would be on the graph, whether it's a line of the graph or whatever it would be. A graph may include solutions that do not appear in the table, and that's why we connect the dots because there are solutions between the dots, but we don't have to find every single point because there would be an infinite number of them. A real-world graph should only show points that make sense for the given situation. So that's where maybe sometimes we don't connect the dots. All right, how do we graph a function rule? We've done a little bit of this. Here's the situation. What is the graph of the function rule y equals negative 2x plus 1? And we're really going to hone in on our skills in this section of graphing functions. So um, here's what I did to do this. I made a table of values, and you may make a table with 3 columns. Sometimes you just make a 2-column one, x and y. This one has the um, work shown in the middle, and then the ordered pair over to the right. So recall that you can pick what the x values are. You always need at least 3 or 4 to show that it's a graph. But this one, I always pick ones that are closer to 0 and that are small. So we have -1, 0, 1, and 2. Those are common ones that I would pick too. Plug them in, each of them in for the x value. Since the x's are our input, we're going to input them in for the x value. Plug it in, plug it in. Maybe you guys remember from earlier on in the year when I showed you that commercial. That's what I think of when we plug in for variables. Um, but it plugs in for the x. So it's -2 times -1 instead of -2 times x plus 1, which is going to get you 3 in this case. So our ordered pair then is -1 and 3. The next one we're going to use is 0. 0 is always an easy one because a lot of times it cancels something out. So 0 times that -2 is 0 plus 1 would be 1. So there's our ordered pair. We have 2 ordered pairs now. And we continue with that. We get 1 and -1, 2 and -3. Those are our other two ordered pairs. Now when you graph them, don't forget the x value. The first number is what tells you where to go left or right, and the y, or the second one, is the up and down. So negative 1 and 3, we go left 1 and then up 3. We have right here. 0, 1, we don't go anywhere to the right or left, and we go up 1. 1, negative 1, we go over 1, positive 1, and then down 1. And then 2, negative 3, we go over to the right 2 and down 3. And that makes a line. So this is a linear function. Connecting the line, the dots, and showing arrows shows that those would be all the possible points that are on there. Now, I like you on your own is think of what steps you would take. How you would explain these. How would you explain these steps to someone else if you were teaching them how to find the graph of a function? All right, here's what I came up with: 4 steps. Choose at least 4 input values. Those are your x values. Now, I don't want to lie to you. You really only need 3. Technically, 3 is enough to make a graph. 4 is better, but 3 is enough. Make a table of values, or t-chart, using those x values and the output values, or y values, that you find when you plug the input values into the function. So it's kind of wordy, but it's what we said right here. When you plug in the input values for the function, use those input values and the output values that you get as your values for your t-chart, and then put those values. Ooh, this doesn't have it right here either. Something disappeared. I wanted this to say write the ordered pairs, graph them, and connect the dots. All right. Not sure how that disappeared. It was there a little bit ago. Um, and then finally, make sure you don't forget to add the arrows, because the graphs do continue forever. So here's what I'd like you to do on your own. I want you to try this one. Get a piece of graph paper or make your own graph. What is the graph of the function rule y equals 1/2 x minus 1? So try this one on your own, please. All right, so here's what I came up with. Hopefully you came up with something similar. I used the x values negative 1, 0, 1, and 2. Plugged in for the function. Got the values negative 1 and 1/2, negative 1, negative 1/2, and 0. And there's my 4 ordered pairs. When I graph those 4 ordered pairs, they're graphed on here. Now, since we're dealing with fractions, they're very close to each other. But it does graph a line, and I connected them and made the arrows continue them on forever. So that's the basic way to graph a function. Those are linear functions. Now let's graph nonlinear functions. So the example here is, what is the graph of each function rule? Here's the function rule we're dealing with. Y is equal to the absolute value of x minus 4. So if you remember absolute value, that means the distance from 0. So absolute value equals distance the number is from 0. All right. If you remember the steps from before, we're going to do the exact same steps, because these are the steps for graphing any function, linear or nonlinear. So we're going to use those steps. First step is to pick 3 or 4 x values. What I'm going to pick is, we'll pick this negative 2, negative 1. We'll do 5, 0, 1, and 2. And we're going to plug them in for our functions. So what's the absolute value of, let's plug it in. Absolute value of negative 2 is what we're plugging in for x. And we subtract 4 from it. Absolute value of negative 2. So that's 2 spots away from 0. So that's positive 2. Remember, absolute value is always going to make it a positive number. So positive 2 minus 4 is actually going to be negative 2 there. So our ordered pair is negative 2, negative 2. Now we plug in negative 1 for the x. Interesting how that happened there. Take the absolute value of that and subtract 4. Absolute value of negative 1 is 1. Minus 4 would be negative 3. So negative 1, negative 3 is our ordered pair. Next one, absolute value of 0. Absolute value of 0 is just 0. That's no distance away from 0. Minus 4 would be negative 4. Absolute value of 1 is 1. Minus 4 would be negative 3 again. Whoops. Interesting that we have another negative 3. What's going on here? Sorry. Alright, and then the absolute value of our last one is 2 minus 4. So that'd be 2. So it's 2 spots away from 0. Minus 4 would be negative 2. So our other ordered pairs here are 0, negative 4. Lots of stuff popping up here. 1, negative 3. And 2, negative 2. And when I graph those, I will have negative 2, negative 2. Right? Down 2 over, 2 down. Negative 1, negative 3. 1 over and 3 down. 0, negative 4. 0 over and 4 down. Now we go positive. So positive 1 and 3 down. Positive 2 and 2 down. When I connect the dots, this is going to make a straight V. Now that's nonlinear. We talked about how if it's a V, it's nonlinear. But that's how you graph an absolute value function. So it's nonlinear. I'm going to give you one more example, and I want you to try this one on your own. It says, what is the graph of the function below? Y equals x squared plus 1. So this is exponential here. All right, so here's what I got. I plugged in those 4 values, got those 4 values out, and there's my ordered pairs, and when I graphed them, it made a U. That's called a parabola. Don't know if we'll be getting into a lot of that this year, but parabolas you'll see in your future as well. All right, graphing real-world functions. So this is the last piece we're going to do here. We'll try to make it quick. When you graph a real-world function, choose appropriate intervals, and this is kind of the different part. You have to make up the intervals for the graph, because chances are they might be high, they might be really low numbers. So it says choose appropriate intervals for the units on the axes. Every interval on the axis should represent the same change in value. If all the data are non-negative, you can just do the first quadrant, which would be the upper right quadrant. So again, that second sentence where if you are making your own intervals, they have to be the same amount apart. So we'll work through this one right here. It says the function rule W equals 146C plus 30,000 represents the total weight. So W is our weight in pounds of a concrete mixer truck that carries cubic feet of concrete. So C is our amount of concrete. If the capacity of the truck is 200 feet cubed, so that's as much as can fit in the truck, what is a reasonable graph of the function rule? So our X or our C value is that independent variable that's inside of our graph. The W is the output, so that's going to be essentially our Y when we're graphing it. And we're using the function rule W equals 146C plus 30,000. So let's plug in, let's pick some numbers. We're going to use some bigger numbers here. I'm going to use, because it can go up to 200, let's use, can't be 0, you can't have a negative weight in there. So you can have 0, 100, and 200. Let's just do 3 values. You need at least 3. We're going to plug into that function rule. So let's do 146 times that C value, which is 0, plus 30,000. I'm going to actually move this all over just a bit so we have some room. That first part is equal to 0, so that whole thing is equal to 30,000. Oops. So the absolute, or the ordered pair would be 0 and 30,000. Interesting. There's a big difference in those two numbers. Second one, we're going to plug in 100, so it's 146 times 100 plus 30,000. That's actually going to equal, so 146 times 100. You can check on a calculator, but they believe it's 14,600. You add 30,000 to that, you're at up to 44,600. So the ordered pair is 144,600. And last one, 200. 200, I think, is going to double that first part again a bit. So 146 times 200 plus 30,000. 106. I think I can do this one in my head. It's going to be 29,200 plus 3,000. So it's going to actually be 59,200. Check that on a calculator if you will. But then your ordered pair would be 259,200. Alright, so here's the tricky part, is labeling the graph. They're all positives, so we can just use the upper right quadrant. Those are all positives. Labeling the graph appropriately is the hard part. So we said they have to go, so this is always 0, but they have to go an equal number apart. So I'm going to actually just I'm going to spread the bottom ones out a little bit. We'll go 0 to 100. They're going to go up by 25, 50, 75. This will be 200. Alright, on the left side, though, we're going to label this a little bit differently because this has to go all the way up to almost 60,000. So let's go, every 4 is going to be, actually, let's do it this way. 5,000, 15,000, 20,000. Yeah, we could do that. So every square is going to be 5,000. So this one will be 20,000. It would be easier if I could move these ordered pairs a little bit. So I think I'm going to do that real quick. I'm going to slide these. Whoops. Did not want all of that. Alright, 20,000 there. 25, 30, 35, 40,000 here. Again, it is very, I don't know why this keeps happening. I've got computer issues here. It's 40,000, 45, 50, 55, 60,000 right here. Now, labels are important too. So the bottom is our C, or that is our concrete, cubic feet of concrete. The W is the weight, so that's going to be the weight over here. And those are in pounds. So it's important to have accurate labels because otherwise the graph will not be accurate. So they have to be spaced out the same amount. So if we go to 0 and 30,000, 0 and 30,000 is right here. 144,600, 144,000, just about right here, right underneath the 45,000. And then 200 and just under 60,000 will be right about here. Look at that. That looks so perfect. It looks like a line. That is a linear function. We have it graphed. We have it figured out. That shows that up to 200 feet cubed of concrete, that truck's going to weigh almost 60,000 pounds. And that's the max that it would weigh. Very interesting. All right, so that's the last part. So I have one closing question that I'd like you to answer. It says, your friend graphs y equals x plus 3 at the right. Describe and correct your friend's error. So what small thing might be incorrect about this graph based on the steps that we came up with? All right, keep thinking about that goal. We'll talk about it next time. All right, have a good one.